let's take a look at position, velocity, and acceleration versus time graphs. So we've already seen that with position versus time graphs, the meaning of the slope of that graph is that it is the velocity. And that's pretty straightforward if you have uniform motion, because in uniform motion, you'll have a linear position versus time graph. And the slope, which is the same as the velocity, is always the same. If you have a not linear position versus time graph, then it's a little more complicated, but we can deal with it. Because if it's not a linear position versus time graph, then it's not uniform motion. So the velocity is changing in some way. But if you wanted to know the velocity at a certain moment, also known as the instantaneous velocity, then you would just look at the graph, the position versus time graph in that moment, draw a tangent line, and if you find the slope of that tangent line, that tells you the instantaneous velocity at that moment. So let's use that idea to go from a position versus time graph to a velocity versus time graph. And these are just going to be sketches. We're not going to worry about numbers. We're not going to worry about magnitudes. We're just going to focus on the shape of the graphs. So let's draw a position versus time graph that looks like this. And you can see that there are linear parts of the graph, but the slope of the graph is not always the same. So what we'll do is we'll split it up. So let's look at that first little segment of the graph. Now that is definitely linear, and in fact, right there, it's flat. So let's see, what would the slope of that graph be? Well, if it's horizontal, then the slope is 0. And the slope of this graph tells us the velocity, so the velocity is 0. And that makes sense, right? In that portion of the graph, the position is constant. The position is not changing. If the position of something is not changing, then it's not moving. It doesn't have a velocity, or its velocity is 0. All right, so we can update our sketch. Now in this next part, you can see that the position is changing pretty rapidly towards being more and more negative. Less and less positive, more and more negative. So the slope is quite negative. So in our velocity versus time graph, the velocity would be quite large and negative. All right. Then in this third segment, again, the graph is horizontal, which means it has a slope of 0, which means that the velocity is 0. In the fourth segment, the position versus time graph has a quite positive slope, so that means that the velocity is quite large and positive. And then in the very last section, it becomes horizontal again. The slope is 0, so the velocity is 0 in that segment. So that velocity versus time graph is a little chunky, got a lot of discontinuities in it, but that makes sense given the position versus time graph. If you look at the position versus time graph, the object has a pretty consistent position, and then it suddenly starts to change, and then it stops again, and then it suddenly starts to change, and then it stops again. And that's reflected in the velocity versus time graph. So yeah, it does look a little strange, but it's telling the same story as the position versus time graph. Let's look at a different example. Let's draw a position versus time graph that's not quite so linear. All right. So we're going to sketch what the velocity versus time graph would look like for this position versus time graph. And the trick here is to think about tangent lines. Think about the slope at different moments in the position versus time graph. And let's start at the beginning. So at the beginning, the position versus time graph is increasing. The tangent line at the beginning would have a positive slope. And if it has a positive slope, that means it's a positive velocity. Okay, now as time goes by, the position versus time graph rises, and then it reaches a maximum. And at that maximum, a tangent line drawn right there would be flat. And if the tangent line is flat, then that means that the instantaneous velocity at that moment is 0. So the velocity is 0 at that moment. And then the position versus time graph starts to decrease, and it decreases more and more rapidly. In other words, the slope is negative, and as time goes by, the slope becomes more and more negative. And remember, slope of a position versus time graph is the velocity. So if the slope is becoming more and more negative, then the velocity is becoming more and more negative. All right, so the velocity versus time graph should start out positive and relatively large, and then as time goes by, the slope remains positive, but it's getting smaller and smaller until it reaches 0 at the same time that the position versus time graph is at its greatest point. And then the velocity becomes more and more negative. Now let's look at a velocity versus time graph. So let's say that we have a velocity versus time graph that is linear. And let's take a moment to think about what that would mean. If it looks like this, then that means that the velocity starts out and it's positive. And as time goes by, the positive velocity becomes greater and greater. So the velocity is changing in this graph. Okay, well, it's a linear graph, so your math teacher would probably want you to calculate the slope if they showed you this. So let's see. If you calculate the slope, let's find 2 points. And to find the slope, that's the ratio of the rise to the run, or the change in y to the change in x, or y2 minus y1 divided by x2 minus x1. Either way, it's the change in the y variable, and here that's the change in the velocity, divided by the change in the time, how much time passes. So it's the ratio of the change in the velocity to how much time it takes. Well, we've seen that before. That's the acceleration. The slope of a velocity versus time graph is the acceleration. So if I wanted to draw the corresponding acceleration versus time graph for this motion, well, the slope is always positive, and the slope is the same everywhere. The slope is constant. So an acceleration versus time graph, well, if the acceleration is the slope of the graph, and the slope is constant and positive, then the acceleration would be constant and positive. So the acceleration versus time graph would be a horizontal line, and it would be positive. And if we had a curved velocity versus time graph, so a velocity versus time graph that's not linear, and we wanted to find the acceleration, it would be very similar to that non-linear position versus time graph when we wanted to find the velocity, right? We would draw a tangent line on the velocity versus time graph, find the slope of that tangent line, and that would tell us the instantaneous acceleration. Now, we're not going to see that very often in this course, but that's how you would do that. The last thing we're going to look at today is the area under the curve. Now, this is related to a mathematical concept called the integral, and we're not going to go over integrals right now. I'll leave that to your math teacher, even though they're really cool. But the idea is that the area under the curve in some graphs tells you something very important. So for example, if we have a velocity versus time graph, and I'll draw it like, if you find the area under the curve, but the area under the curve in a velocity versus time graph tells you the displacement. So let's pick 2 different times, t1 and t2. If you find the area under the curve between those 2 times, that will tell you the displacement of the object between those 2 times. And the area under the curve is a little bit of a misnomer. It's really the area between the curve and the horizontal axis, and I'll shade that in here. The other weird thing is that the area under the curve, if it's above the horizontal axis, it's considered positive area. And if it's below the horizontal axis, it's considered negative area. But if you determine how much area is above and how much area is below, and you add those 2 together, remember above the axis area is positive, below the axis area is negative, but if you add those 2 together, that will tell you the displacement of the object. And if that seems like magic, it's not. It can be explained, but we're not going to go through the mathematical steps to explain it right now. We're just going to use it. Okay, if you have an acceleration versus time graph, and you find the area under an acceleration versus time graph, that tells you the change in the velocity of the object. Now, you got to be careful. The area under the curve in an acceleration versus time graph does not tell you the velocity of the object. It tells you the change in the velocity of the object. And it's similar to when we found the area under the curve in a velocity versus time graph. If you have area that's above the horizontal axis, it's considered positive. And if you have area below the horizontal axis, it's considered negative. So to summarize, if you have a position versus time graph, the slope of that graph tells you the velocity. If you have a velocity versus time graph, the slope of that graph tells you the acceleration. If you have a velocity versus time graph, the area under the curve tells you the displacement. And if you have an acceleration versus time graph, the area under the curve tells you the change in the velocity.